Hello, everyone, and welcome to today's webinar, Glassware Washers and Result Reliability, Wash Worry Away. I am Jennifer Woods of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by LabConCo. To learn more, visit labconco.com. Let's get started. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, click on the Support tab found at the top right of the presentation window, or report your problem by clicking on the Ask a Question box located on the far left of your screen. This presentation is educational and thus offers continuing education credits. Please click on the Continuing Education Credits tab located at the top right of the presentation window and follow the process to obtain your credits. I now present today's speaker, Jordan Henderson, Product Manager at LabConCo Corporation. For a complete biography on our speaker, please visit the Biography tab at the top of your screen. Jordan, you may now begin your presentation.
Hi, my name is Jordan Henderson. I'm the product manager here at LabConCo for glassware washers and water purification. Today, we're going to have a little presentation over glassware washers and result reliability and washing away any worry that may be encountered in various laboratory environments. On the agenda specifically for today, we're going to discuss the impact and potential sources of carryover contamination, identify and discuss highly sensitive analytical methods that will be and could be impacted by sample carryover, identify and discuss common laboratory contaminants, really the causes of potential contamination, and then we're going to discuss how implementing a laboratory glassware washer can help provide consistent, repeatable, reliable results. So really the first question to discuss is, what is carryover? So this is just a basic term used to describe a type of sample contamination. So really there are two types when discussing sample contamination. You have sample to sample, and sample to sample is when a previous sample is actually present in subsequent runs. A lot of the times this will look like ghost peaks and Blake runs after the subsequent analysis. This will also result in potential false positives. The other type of sample contamination is going to be your reagent to sample contamination. This is more commonly found on high output continuous run instrumentation. So really the next question to ask is, why as a laboratory professional should I be concerned with sample contamination? Well, really, I mean, it's just a very serious issue when it comes to the currency of the laboratory. The quality of your results is paramount. Obviously, sample contamination can result in errors in analysis. If you get enough of those to stack up on you, it really calls into question the reliability of the results that you and your laboratory is putting out, and that was going to really take a hit towards your laboratory's quality. Finally, well, when it comes to decreased quality and reliability, that's going to essentially cost laboratories time and money. In a previous life, I worked as a clinical laboratory scientist here at local hospitals here in the Kansas City area, and we were constantly concerned with sample carryover, reagent carryover, how it impacted the quality of results that we were putting out on a daily basis. From a purely clinical standpoint, it could impact just the overall cost of consumables for sample collection, time and money it takes for med techs and clinical coordinators to identify sources of those contaminations, retraining, and then even you're putting out results that are affecting patient treatments and patient outcomes, and that can affect their bottom line as well. So I know that's a specific example, but I think it's the overarching message is important to outline that when you're introducing variability and contaminants into highly sensitive analytical methods, that tends to snowball the exact same way. So it's important to identify potential sources where contamination can essentially show up. And the first place I would want to look at is just the general laboratory environment. There are specific environmental factors such as humidity, temperature, and the presence of light that can adversely affect samples that you're going to use for analysis. Certain molecules and compounds may try to grab excess moisture in the air, which could have negative effects on the quality of your results. Temperature will also play a role in the accuracy and percentage yield that you're looking for when it comes to certain reactions. Low thermically labile molecules generally will break down in the presence of higher temperatures. Then there are also molecules and compounds that are photosensitive. Some examples of these are some drug compounds like the digoxin and diazepam. Also, vitamins like folic acid and other B vitamins tend to be photosensitive. There are also bolinogens, urobolinogen, porphyrobolinogens that will break down in the presence of light. So it's important to obviously protect those from too much light. So really the overarching point of this is to be aware of your laboratory environment, temperature, presence of light, humidity, all those things, so we can remove variables when it comes to analysis. Another potential source of contamination is the use of substandard reagents. Ultimately, when using substandard reagents, this just presents an opportunity to present additional impurities into your reaction or your workflows during your analysis. Oftentimes, laboratory professionals will use old or expired reagents. Obviously, this isn't recommended. The use of calibrators in QC material obviously will justify whether or not the reagents that you're using in the process are within the realm of usability. Also, fair to say, improper reagent preparation is also a source of contamination. A prime example of this is in the lab, I would make up anti-10A or other coagulation QC calibrators. That stuff was very specific, it had a very short stability, and it was very receptive to how specific you made or followed the package instructions to make up those QC calibrators. That obviously can vary from person to person, and Tech A versus Tech B can make something entirely different, and that could produce a different result for you. Finally, oftentimes laboratories have to make cost-cutting measures. Sometimes that is purchasing reagents from a less reputable dealer. Using less quality products obviously will impact the quality of your reaction as well, so just something to be aware of. Another place to look when it comes to potential sources of contamination are going to be laboratory professionals themselves. First and foremost, the lack of PPE being used in laboratories could potentially lead to additional contamination. not using rubber gloves, face shields, disposable masks, lab coats, all can lead to the introduction of fibers in samples, coughing, so microbes, other aerosols, things like that. As I mentioned before, another source of contamination are just the variation between tech to tech and how workflows are performed, reagents are reconstituted, QC calibration is run. Also worth mentioning that instrument contamination, and by this I'm really meaning how pipettes, other volumetric things are used when you're making up these reagents are used. They shouldn't be shared. Also, technique is very important. If you're bulb pipetting, you can essentially aspirate up reagent from one workflow and then use that same bulb to draw up an additional reagent, and that passes that along into the analysis, introducing that reagent to sample contamination. Also worth mentioning that visitor entry is something to be aware of. That just allows for an increased potential exposure for the outside environment. So again, always be aware of just limiting certain factors when it comes to really protecting your sample from potential contaminants. Now we get to the crux of it. Samples are often stored, transported. Reagents are mixed, stored, transported in reusable borosilicate glassware. So all of those potential contaminants that I previously mentioned are being funneled into these things. Residual chemical contamination, for example, previous reagent remaining in this glassware, and then new reagent is being placed in, and we're then contaminating that reagent with old reagent and using it to do analysis. And then residual sample contamination as well, the same principle. Dirty glassware that had a previous sample in it isn't getting cleaned enough. Then we put a new sample in, and then that's going to affect the result quality later on down the road. So we've discussed sources of contamination. Now I think it's important to discuss some of those highly sensitive laboratory procedures that are going to be severely impacted by residual contaminants. The first three, so high-performance liquid chromatography, ultra-high-performance liquid chromatography, and supercritical fluid chromatography are all liquid chromatography methods that are still operating on the same basic principle. Then we throw in mass spectrometry, which combined with liquid chromatography principles is a highly analytical, highly sensitive method. And then, of course, polymerase chain reaction is also very sensitive to contamination. So high-performance liquid chromatography is just an analytical technique used to separate, identify, and quantify compounds in a mixture. This is generally found in analytical laboratories. So the general HPLC procedure involves moving solvents containing an unknown mixture, which is also known as the mobile phase, through columns containing absorbent materials, which is known as the stationary phase. This will lead to that mixture interacting with that stationary phase, and then separating out compounds for identification and quantification. This is commonly found in research, medical, and manufacturing fields. Moving on to the ultra-high performance liquid chromatography. This is still going to use the same basic principles of mobile phases and stationary phases, but they use a higher pressure range. The higher pressure range is good for pulling out lighter molecules and increasing purity. This is all commonly found and used in pharmaceutical fields, medical fields, and then in research as well. Moving on to the supercritical fluid chromatography. Again, same principle as the HPLC. However, the mobile phase leverages CO2. This is used in the analysis and purification of low to moderate molecular weight molecules, thermally labile molecules as well. Again, those are just molecules that tend to break down in the presence of high heat. And then chiral molecules. And a chiral compound or molecule is just a superimposed molecule that is a mirror image of itself. A good example of this is going to be ibuprofen or warfarin, which is an anticoagulant. This is a less used technique, but it's mostly going to be found in the pharmaceutical industry. All right, moving on, we are now going to marry those liquid chromatography techniques with mass spectrometry. Mass spectrometry is really just an analytical technique that measures mass to a charge ratio. They accomplish this by manipulating the motion of the ions by using electric or magnetic fields. So you can use this technique for a variety of compounds. They can be biochemical in nature, organic or inorganic, so it really just covers everything. This is commonly found and used in biotechnology, environmental fields, food and agriculture fields, and then cosmetic and consumer industries. The final sensitive technique that we're going to go over is going to be polymerase chain reaction. This is a simple technique where laboratory professionals are trying to amplify a target sequence of DNA and RNA. Really, the two most common types are real-time and quantitative, and those are just really characterized as endpoint detection methods. They're used to analyze various pathogens and viruses. Some pathogens include E. coli and Salmonella. Some viruses could potentially be hepatitis, HIV, norovirus, even some molecular testing like JAK2s use PCR. This method is commonly found in biotech, medical, food industry, and research settings. All right, so now that we've talked about those sensitive analytical methods, I think it's important to really kind of just identify some pretty basic and common contaminants that we can find throughout the laboratory. So on a very broad level, the residual contaminants on glassware tend to or can be solvents, inorganic, organic, polar, non-polar solvents. So anything that you use to store in a beaker. They could be acids or bases, weak acids and weak bases specifically. Also could be waxes and other lipid-based compounds. Waxes are generally produced during alcohol extractions. And then also it's worth mentioning detergent can be a contaminant as well. Other more specific contaminants could be fatty or proteinous material. These tend to be contaminants consisting of plant and animal-based samples. A lot of the times you'll see this from Keldol acid digestions. Also, you can see them from crude fat and fiber analysis. So this is going to be real big in the food and ag and the food industries. Essentially, you're just taking samples, boiling them in acid, and then titrating them out to get the nitrogen percentage. So when those samples are undigested and residual acid remains, obviously, if those flasks are used again and they're not effectively cleaned, they can have a negative impact on the result quality that's produced. All right, so now moving on to really burnt and charred residues as well. So this is, again, a very broad group of contaminants, but it's something that laboratories run into a lot. These burnt and charred solutions, mixtures, obviously will result in result quality issues if not cleaned appropriately. They tend to be sticky, very hard to clean. And removing these residues often require a repeatable cleaning workflow. So I would picture, a busy grad student running around in a research setting, trying to do multiple things at once, and they're heating up a solution, and then they step away for what seems like a minute, but it's actually a little bit longer, and then they forget about it, and then that solution is then evaporated, and it's caked on glassware. So just be aware that that does happen, and we just need to be able to account for that and clean it appropriately so we can reuse that glassware at a later date. Another contaminant to consider are microbes and bacteria. This type of contaminant affects the useful life of reagents and buffers due to the buildup of these colonies of mold and other bacteria. Potential effects range from having an impact on stability of suspensions and solutions. They could even act as catalysts or inhibitors to various reactions. They also can lead to the formation of unwanted reaction products and additional impurities. So when it comes to dealing with this type of contaminant, it's always important to identify, when it comes to glassware washers, the maximum heat, water temperature, and drying temperature. But also, if you're talking from a sterility standpoint, when in doubt, it's always good to autoclave. Just to remind those, for dry heat, 160 degrees Celsius for 1 hour should do the trick. But when using a steam autoclave, 121 to 140 degrees Celsius, the target temperature for that. I had mentioned previously that detergent could also be a common contaminant. Residual detergent on glassware can yield undesirable analysis results as well. Detergents have a very wide range of pHs, all the way down to 2, so highly acidic, to like our detergent is 13 to 14, so it's considered pretty alkaline. Those changes in pH can affect the reaction environment, which will yield undesirable results. They also consist of varying chemical compounds, so you're just, again, introducing potential impurities into reactions, which can have effect on your results. And then also, some of these detergents are enzymatic in nature, so they can also drastically affect the outcome of your reaction that you're trying to control. When in doubt, less is more. There are a lot of people that will call it, that I've spoken with, saying, hey, we're having a lot of residue on our glassware, and that's due to putting in too much detergent. So more detergent doesn't always equal more clean. So moving on, we're going to get into the specifics of detergent, just because detergent and glassware washers have a very synergistic relationship. So when identifying the important parts of detergent, the first one that comes to mind is the surfactants. And what a surfactant is in detergent are molecules that consist of hydrophilic tails and hydrophobic heads, and essentially this is going to reduce the surface tension of the water. Moving on, the next component of detergent is something called a carrier, and this aids in dissolving soils and other contaminants. Next are the chelators. This molecule basically binds to free metal ions in the water. So this, if you would think of like water hardness, the chelators are going to help with that. And then the last component of detergent is something called builders. Generally, these help emulsify, buffer, and soften contaminants that are going to be left on glassware. Also, generally speaking about detergents, it's important to note that if you do have a specific type of contaminant, there are certain pH levels that are going to better suit cleaning. When trying to clean heavy scales, pH of 0 to 2, so very acidic is recommended. For salts, oxides, and metallics, 2 to 5.5 is generally acceptable, so mildly acidic. For the more neutral pH range, that's going to be light oils and particulates. Mild alkaline detergents, so 8.5 to 11, are going to be for your slightly hardy oils and films. More alkaline, so that 11 to 12.5 are going to be for natural oils, fats, and resins. And then heavy greases and soils are going to be best cleaned at a pH of 12.5 or higher. So next, we've talked about contaminants, we've talked about detergents or selecting the right detergents. It's important to understand the substrate that you're trying to clean those contaminants off of. There are various substrate types. More or less, most laboratories are really just going to be concerned with the plastic, stainless steel, and glass, but I did want to mention aluminum and other soft metals. These tend to be best washed with detergents in a pH range of 2.5 to 9.5. Moving on to mild steel, really the thing to focus on there is that the corrosion is controlled by completely rinsing and drying these pieces. Moving on to plastics, not surprisingly, plastics can stand up to a broader range of aqueous cleaners. Stainless steel generally are going to be best cleaned in alkaline detergents ranging from pH of 10 to 14. And then glass, specifically borosilicate glass, again, very resistant, can stand up to a wide range of detergents. So really the next question is, why should my laboratory or any laboratory implement a glassware washer? It's always important to keep in mind that these glassware washers were designed with laboratories in mind. These washers generally consist of pretty robust, hardy components that can provide greater performance, whether it be the wash pump, drain pump, spray arms. With these better performing components, it also comes with increased reliability. They can withstand the fluctuations in the high heat needed to adequately clean glassware. Also, this provides an opportunity to standardize and automate the messy, unwanted task of cleaning glassware. Also, the construction of these units is built to withstand harsh laboratory conditions and environments. And also, worth mentioning, this limits the exposure for laboratory professionals to incur workplace injuries with broken glass. So really, what questions should you be asking if you're in the market for buying a new glassware washer, updating an old one? Really, the first thing you should look for is the incorporation of 3 or 4 stainless steel or better. 3 or 4 would be basically the gold standard. I do see some manufacturers that offer 316 stainless steel. With that being said, next, you want to see a less of a dependence on plastic components. Plastic components obviously tend to break down much faster than steel. When it comes to physical components, such as circulation pumps, you're really looking for the circulation rate. I would say the baseline gold standard circulation rate was going to be around 96 gallons per minute. Some manufacturers do have a separate drain pump to drain the water versus using the same pump to drain and circulate. For those that are really concerned about contamination, I would explore the option of finding manufacturers that can separate those two out. When it comes to water temperature, the minimum temperature you want to see to sanitize is 74 degrees Celsius. Several manufacturers can easily get to 82 degrees Celsius, 93 degrees Celsius, and can even go to as high as 99 degrees Celsius. So it's really whatever you're looking for to really penetrate, soften, and remove those contaminants on that glassware. Other things to consider are going to be direct injection. And this is just really just a commentary on what kind of glassware you're trying to wash. Some laboratories are going to rely heavily on wide mouth glassware, and that could be beakers, bowls, other things like that, whereas other laboratories may have more Erlenmeyer flask, more Keldall flask, things that are narrow necking in nature. So the washing method has to change. Spray arms, the upper and lower, will do a great job with beakers. For those narrow neck glasswares, you're going to look for manufacturers that can offer direct injection washing and drying. Not only will that make sure that inside of those flasks are clean, but it will make sure that inside of those flasks are also dry. When it comes to drying temperatures, it's also fair to ask to see a drying temperature of 70 to 80 degrees Celsius, and this will quickly dry glassware completely. Next, when it comes to even pure water rinses, to make sure you're getting any residual contaminants off that glassware, it's definitely a question that you need to ask, do I need this? The benefit of implementing pure water rinses is that it's another level or another step taken to completely remove contaminants from glassware to ensure that when these are reused, that you don't have to worry about introducing contaminants to your workflows. Oftentimes, pure water pumps will come as pressurized or non-pressurized. Really, the only thing to be aware of there is that you need to have a pressurized source of pure water. For those leveraging non-pressurized pumps, you can use carboys or storage bladders or really whatever, however you store your tank. Next, it's always fair to ask the question, how am I going to interact with this, and how is that experience going to help me on a daily basis? A lot of manufacturers are updating, and we're moving away from push button controls, and we're starting with touch screens that offer robust features that are very user friendly, and it makes sense to use it the way, or it's instinctive on how to use the washer. By implementing updated controls, this allows several manufacturers to provide extensive data logging and export features just for documentation, which, again, very important when proving or recording any results that you may need to at a later date. Also, it's worth mentioning that washers should have clear alarms. You shouldn't have to essentially go find the user manual, reference a table just to find out what alarm it is. That should be clear, present, and you should know exactly what you're dealing with the second you're interacting with that unit. Also worth mentioning, if you have any specific requirements or special features that you need, oftentimes HEPA filter drying, or I'm sorry, HEPA filter force air drying is an option that can be added onto washers, and that's just going to go ahead and filter out potential air contaminants during that drying process. Also, for those that need to have or keep an eye on water quality, conductivity sensing for measuring water quality is a feature that is commonly used and leveraged. Also, it's worth mentioning that water softeners are being incorporated into these washers as well for those sites that have water supply quality issues. So if they have like super hard water. Moving on, no washer is complete without a robust ecosystem of accessories. These accessories are going to help maximize cleanability, help you store as much glassware to make sure it's oriented the correct way so you get the correct cleaning. Also, it will help with specialty glassware like graduated cylinders and volumetric pipettes to make sure those are cleaned and reusable. All right, so just to recap on my final slide, you guys, I think it's important to identify potential sources of contamination, what kind of contamination you can run into, what you're trying to wash from a substrate perspective, and then why implementing a glassware washer can help save a laboratory professional's time, automating and standardizing the messy, unwanted tasks of cleaning glassware, helping produce repeatable, reliable cleanability when it comes to your glassware, standardizing that resource consumption, so from a water and electric standpoint, and then limiting potential exposure to workplace injuries as well. Again, thank you so much for your guys' time. I'm ready to field any questions that you guys may have when it comes to glassware washing.
Thank you, Jordan, for that informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you would like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many of your questions as we have time for. Now let's get started. Okay, our first question is, what option do you have for washing pipettes?
So that's a great question. Really, most glassware manufacturers are going to have specialized inserts for pipettes. This can range from gasketed tubes to gasketed blocks that actually directly connect to the glassware washer racks. That'll provide that direct injection of water and air for washing and drying. So that's generally how most manufacturers handle it.
Okay, thank you. Got another question here. What are some common contaminants found on labware?
Some common contaminants are going to be obviously residual reagents and actual samples that you are testing in. A lot of the times I do notice glassware that's generally used to heat, boil various chemical mixtures tends to be pretty sticky and gunky on that glassware, so it's obviously important to get that off if we are going to reuse that glassware. Me also being the product manager of our Keldol solution, I do manage to see a lot of Keldol flasks that tend to contain a lot of fibrous and gunky material from that acid digestion process. So yeah, those are just a few of the common contaminants that I've seen in my experience.
Okay, we've got another question here. What is a contaminant-sensitive method commonly used in a laboratory setting?
So a contaminant-sensitive method that's going to be used in a laboratory setting most likely is going to be your HPLC. That's really a pretty robust technique that can be used in a variety of markets and sectors to do a variety of different workflows. So that workflow can also be used to actually validate cleaning procedures as well for those that need to do that to really make sure that they're using contaminant-free glassware. So yeah.
Okay, thank you, Jordan. I have another question. This is the last question from the audience. What role does detergent play in removing labware contaminants?
Another great question. So really, when it comes to how detergent and glassware washers play, it's really kind of a synergistic relationship. Obviously, that glassware washer is going to be spraying water, heating water. It really used to dislodge any sticky contaminants on that glassware. However, that detergent is also going to play a key role into breaking down and emulsifying and scrubbing those stubborn contaminants that are baked on, cooked on, boiled on in that glassware. So it's really kind of the 1-2 punch that laboratories really need when trying to clean that dirty glassware and get reliably clean glassware on a daily basis.
Great, thank you. I've got another question here from the audience. What are some methods for raising or lowering the pH of a wash or rinse, especially to become more basal? For lowering the pH of the rinse, it's important to always use an acid neutralizing rinse. A lot of the times
generally wash water tends to get a little more acidic, obviously when you're washing contaminants off of glassware, so it's important to neutralize that during the rinse cycle just by leveraging acid neutralizing rinses.
Okay, thank you, Jordan. I have another question here from the audience. Can I wash plastic items?
Yeah, so it's always important to know what you can and can't wash. Obviously, plastic is going to be a little more sensitive to the higher temperatures. It's always important to ask that question, especially to who or where you got that plastic from, to see if there are any specific temperature requirements. For the most part, plastic polymers and those plastic utensils that you can use and that you can also reuse generally do a pretty good job nowadays of standing up to high pressure washing and high temperature heating and drying as well. So.
Thank you, Jordan. That's the last of our questions. So I want to thank you for your time today. Do you have any final comments for our audience?
No, I just wanted to, again, reiterate thank you for your time today. It was a pleasure to present to you guys. I hope you guys learned something, found it informative. And then, of course, if you have any additional questions, please don't hesitate to reach out to us or visit our website at www.labconco.com, and we'd be more than happy to help you out.
Well, thank you again, Jordan, for your time today and for your important research. We would also like to thank LabRoots and our sponsor, LabConCo, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. A survey will be displayed on your screen shortly. Your participation is greatly appreciated. Until next time, goodbye.